All right, why don't we get started? Today, it's my pleasure to introduce Professor Alireza Khaligh from University of Maryland to give us a talk about transportation electrification and power electronics. Alireza Khaligh is one of the experts that can really leverage the state-of-the-art in power electronics into transportation electrification and use the applications of transportation electrification to advance the fundamentals of power electronics. Professor Alireza Khaligh's group worked broadly across electric vehicles, more electric airplanes, power system on ships, and many other applications. He has won many awards from both the IEEE Transportation Electrification Society and Power Electronics Society. With this, let's welcome Professor Alireza Khaligh.
Thank you, everyone, and thank you, Minji, for the introduction. It's my pleasure to be here to give this presentation about my research. I don't know if, can everybody hear me well? Okay, very good. So I'm going to try to give a more, I know that the only people that there are not many big group in power electronics, so most of the people are different, like diverse group of people who work on energy-related subject. So my research is going to be, my presentation is going to be more on general aspects. So I'm not going to go into equations, how to drive equations, how to design, how to choose an inductor, how to choose a capacitor, how to design or draw a PCB. So it's going to be more general so that it's better understandable for a big group of audience. So I joined University of Maryland at College Park in 2011. And all I'm presenting here is what we have done in the last not 7 years, 5 years, because we are starting a lot of new projects which I'm not, we're just starting them, so I don't have a lot of results to present on those. I guess you're familiar with the University of Maryland. I just want to give an overview. We are just 7 miles northeast Washington, D.C. You're more than welcome to come visit us anytime. And again, it's just 15 minutes from northeast D.C. This is my current research group. I have right now 10 PhD students, 1 postdoc, hired 2 more postdocs joining. So we are 13 members, and these are some of my group's alumni. In the last 7 years, they have joined. We have graduated 9 PhD students, 10 master's students, and a lot of undergraduate, 39 undergraduate students. They have worked with us, and now they work in different sectors. They're either PhD students in different institutions or our own research group. About now, let's move on to power electronics. So power electronics is going through a major restructuring. Traditionally, a lot of universities, they didn't even have power electronic program, but now power electronic is going through a major restructuring. A lot of new subjects, new emerging technologies are happening, like wide bandgap devices, like silicon carbide, wide bandgap devices, like gallium nitride, diamond semiconductors. So they are pushing power electronics to go through a complete restructuring, right? So we need, when we are introducing all these new semiconductors, we need also high reliability, low ESR capacitors, magnetic components that they can operate in high frequencies, like the stuff that Professor Minji Chen is working on, going up to, like 30 megahertz switching frequencies. They need completely new circuit design, new gate driving algorithms, new schematic design. You need to care about parasitics even more. So there are tons of new stuff that needs to be invented and investigated in power electronics. So besides emerging technology, there are a lot of new emerging design techniques which are being investigated in the power electronic community, which people are looking multi-objective optimization. Traditionally, the way that people have designed power electronic converters has been based on heuristics and based on experience that they had, right? Best practice experiences. But now, with all these different components being part of power electronic, we need to have really optimized power electronic circuit design, considering not only component, but also considering even parasitics and PCB design, which is, again, it's a complicated thing. Also, design for reliability. It depends on what you're designing. Design for packaging. These are very important as the U.S. Department of Energy is pushing towards, higher power densities, better efficiencies, higher specific energies, and lower cost. And design for, in fact, manufacturing is another thing is there that we can add. Design for excellence and design for manufacturing. So these are all new things which are happening in power electronics. And there are tons of applications. And then not only there are tons of applications, but new applications are coming to play. So in terms of applications, you can see these are some of the applications that came to my mind, and I have listed them, but I'm sure there are even more. For example, in drilling applications, now power electronics is playing a role in even like oil companies. They're interested in designing power electronics for, going like to really high pressure, high speed electric motors and power electronics and drives for those things. And we can talk more and more about those. So now our research at the University of Maryland has been focused on design of the modeling, design optimization of power electronic interfaces for transportation electrification. When I talk about transportation electrification, my research has done focus on plug-in electric vehicle cars. We have done a lot of research on onboard chargers, off-board chargers, and also we have done a hybrid energy storage systems. I'm going to talk about the onboard charger in this presentation. I'm not going to go into a hybrid energy storage system. Also, we've done a lot of work. We've been sponsored by the Boeing. I think there are only 2 universities that Boeing has been working with them, and we are one of the, in power electronics sector, I'm mentioning. We are one of the groups that we have worked on regulated transformer rectifier units for next generation 787, and they are considering to build a new plane, which this technology they are evaluating to consider for the next Boeing aircraft. Also, we do some work on high reliable and efficient and low-cost PV microinverters. So we are looking into bringing the cost of microinverters by 3-fold in next 3 to 5 years. And also, we are looking into designing something which is going to be manufacturable and low cost, and we want to improve the reliability to 25,000 mean time to failure. Also, we've done some work which I'm going to briefly touch base on miniaturization of power electronics for micro-robotics, energy harvesting, Internet of Things, data centers, and other stuff that are like happening. So my talk is going to be mainly focused on this topic mainly, but I'm going to a little bit also try to show stuff we've done in this subject at the end, just briefly go through them. So power electronic, if you look at the automotive industry, I know a lot of people there, they don't like electric cars still. And I remember a few years ago, I was in a talk that this guy, there was a group of people, they wanted an e-cab, electric cab company. And people, they were sitting in the board of the Arlington County, and they invited me as an expert to vote there. This was like 5 years ago. And the guy wanted to build all the fast charging stations in Arlington County. Like many people, they voted against it, and it was not approved. And it was, in my opinion, unfortunate. And the guy was even saying, if it's not successful, I'm going to leave all these things for the city for free. I'm going to walk away. But of course, there are many cab companies, many that it's going to be against their, business model. So of course, I can see those things happen. Unfortunate. But anyways. Looking at the projections in 2017, these are I did like a list of the electric car sales, top-selling electric cars in North America in 2017. You can see Tesla Model S has sold about 27,000 cars. And if you look at the plug-in hybrid electric car in 2017, you can see that Toyota Prius Prime has been sold more than 20,000 of those. And in my opinion, electric car is about to pass the tipping point, and it's gonna go mainstream, but when, it's a matter of question, and then see how it depends on the cost of batteries, and more important, another important factor is the cost of the power electronic and weight of the power electronic. People only talk about batteries because for them say, oh, batteries are big, batteries contribute to 30% of the cost of the car and then 30% of the weight of the car, but in my opinion, besides batteries, power electronics is very important and has not gained enough attention. That's the thing. If you look at, I was in fact in DOE Oak Ridge National Lab, and I saw a very interesting chart showing that the cost of the battery has become 1/5 in the last, I think, in the last 10 years. And the energy density of the battery has gone up 5 times, 5-fold. But that hasn't happened to power electronics. And there are tons of power electronic components. Before talking about power electronics about the car, let's look into mileage range of the cars. So I looked into most of the popular cars in the market right now, and I found out, okay, the mileage-wise, electric cars, they range from 85 miles to 335 miles, right? In my opinion, we need to pass 300 miles. This is a good threshold so that we can say, okay, an electric car can drive a reasonable amount. This is nothing, right? but we should also pay attention to the fact that even though this is 85 miles, but the charge speed is also going to be faster, right? But in this case, your charging speed could be longer. I'm not going to talk about so much on fast chargers in here, but we can talk about fast chargers as well. And right now, DOE has a program on the extreme fast charging to make sure that you can charge your car in 10 minutes. So when we talk about 10 minutes doesn't mean you will fully charge your battery in 10 minutes. And I don't think you need to fully charge your battery in 10 minutes to drive. If you look at the way that you charge the lithium-ion batteries, again, I'm not a battery person, I'm more on power electronics charging. The way that we have been taught how you can charge a battery is you do constant, let's say constant current, constant power, constant voltage, or constant current, constant voltage. So during the constant current charging, you normally fill the battery up to 80% of the state of the charge. And that is good enough for you, and also is faster. The rest 20% will take much longer time. So you can get to that 80% in 10 minutes and then go the rest. And again, if you're familiar, I don't think I have a slide on the standards of the ACEE 1772 on looking at what are the different levels of charging. But normally anything below 1.92 kilowatt is level 1 charging, that you can charge your car using a simple outlet in your home or in your garage. Anything more than 1.92 up to 19.2 is level 2 charging, that you need to have a special outlet, maybe those like plugs that you have for your washer dryer. Those are like 240, maybe those kind of thing, maybe 2 of them in parallel. Those will give you, most cars they have 6.6 or 7.6, some of them even, in fact, a little bit higher. Maybe people are looking to 11 kilowatt onboard chargers. And then anything beyond 19.2 or 20 kilowatt is off-board, like fast charger. But right now, to get that 80% charge in 10 minutes, people are looking at
350 kilowatt charge stations. So, these cars, I looked into what I was interested to see. What is their onboard power rate, charge rating? That's this is a separate topic, not off-board charge, right? Off-board charge can do anything beyond 19.2 and can charge your battery quickly. But any car, anyway, needs to have an onboard charger. For convenience, right? Wherever you go, you need to have an onboard charger. So if you look at the onboard EVs, you will see most of them, they have 6.6 kilowatt onboard chargers, some of them up to 17.2 or even 19.2. Tesla Model S and Model X. So then also we looked into plug-in hybrid cars and see what is their onboard charging right now. They're mostly 3.3. But the industry is moving a little bit higher power levels. Onboard chargers now is moving toward 11 kilowatt onboard for the electric vehicles, and for plug-in hybrid electric vehicles, they are moving towards 6.6 kilowatts. So everything is going one level beyond. So there are tons of opportunities for power electronic people in this environment. What are the opportunities that we have? We have the opportunity to use wide bandgap power electronic for the propulsion inverter. That is a power electronic component which is heavy, which is expensive, and sometimes its performance could be significantly improved. Also chargers. Also, besides that, we need a propulsion DC-DC converter, another component which is going to contribute to the weight of these cars. Energy storage system. If you have a battery, you need a battery management system, battery equalization system, and besides that, if you have a hybrid energy storage system, you have a battery, you have a supercapacitor, you have another DC-DC converter in the middle. So additional contribution. And then electric machines. Electric machines are part of power electronic components, right? Like, when we talk about power electronics, we mean power electronic electric machines and electric drives. And now permanent magnet synchronous machines are very important, and now research community is looking into going through less. It's very difficult to go completely permanent magnet-free machines, which are switch lossless machines, but people are looking at a hybrid kind of permanent magnet machine, so you can less permanent magnets because they are rare earth material, and then move towards kind of combination of high-performance machines. So that's another research area that mostly people at the University of Wisconsin-Madison, they are one of the leading groups working in this area. When we talk about off-board chargers, I said onboard and off-board chargers, and also wireless charging are becoming important. Wireless charging is also not only for electric vehicles, there are tons of applications. Wireless charging is going everywhere, wireless everything, right? That the research that's for example, NGs we did here is also a lot of multiplication in different applications. So this is just electric vehicle. If you just focus on electric vehicle, I showed so many applications. If you focus on electric vehicle, there's tons of opportunities for power electronics. Now think about all these areas. And of course, auxiliary power modules is another component which needs to be investigated and improved significantly. So my perspective for next generation onboard chargers, these are two of the proof of concept that have been designed in my lab at Maryland. These are onboard chargers that we have designed. One of these, this topology is, I'll briefly explain what it, I'll move on and explain a little bit later. I wanted to show the topology, how does it work. But I want to give my perspective for next generation, only focus on onboard chargers before I move on and talk about the circuit topologies. So in terms of onboard chargers, first of all, right now we don't have any onboard charger which is bidirectional in the market. So one of the areas which we need to have bidirectional onboard charger for grid support. That's the first thing we need. Besides that, we need to have integrated magnetic components. If you look at the design of onboard chargers, the way that they design the DC-DC stage, normally they use like CLLC converter, and the CLLC converters, they have an additional magnetic components which is larger than leakage inductor, and they use it as a resonant inductor to create resonance and create zero voltage switching in your switches when you're turning on and turning off any switch in your circuit, in your power electronic circuit. Majority of the loss come from the switching losses, right? So we want to minimize those, improve the efficiency. So you have additional resonant inductor there. And now if that we can, and then you have a transformer, for example, for galvanic switch. If you can integrate these two components into single component, that will reduce your weight, because magnetic components, they contribute to the weight and efficiency loss in the power center. So we need to look into the converters that they have integrated magnetic components or structures that they can provide us. Besides that, we need to have, in my opinion, chargers that they are capable of charging deeply depleted battery packs. I was visiting a research group, which I don't want to name them, but it was interesting. They had I don't know how, somehow they got a donation of Tesla Roadster. They had a donation of Tesla Roadster, and I saw it sitting in the corner of the lab. I'm like, what are you doing this? This is so awesome. I mean, I wish I had this in my lab. They said, yeah, but it's useless. I'm like, why? Because the battery is dead. And if you want to change the battery, it's going to cost so much. So I think if we have chargers, and then I visited Ford, and when I was visiting Ford, I mentioned in one of my presentations to them, it's a very important idea, in my opinion, that we can have chargers that they can charge deeply depleted batteries. And if you, let's say a single lithium cell, if the lithium voltage goes, normally they use it from 2.5 to 4.2, right? If I'm not right. Again, I'm not a battery guy. But if the battery voltage drops to 1 volt, apparently they say it's dead battery, right? You cannot charge it with normal chargers. So what if we can have chargers that they can charge from 1 volt, build up load? I don't care about the efficiency. The efficiency will be low, but at least we can charge it instead of being, taking your car. And then I was told we don't want that because it's going to cost us extra money, and then at least the car owner should take it to the dealership, and the dealership will take care of it. I agree on that from their perspective, but in my opinion, if we can provide that without any additional cost, free, if we just change the control algorithm, why not? So we are a research community, and we need to investigate this approach. And also we need to investigate ways to improve the efficiency. So most of the chargers people design stuff, or they invent new chargers that come up in new topology, say, oh, my charger efficiency is 92.8%. But then, unfortunately, that only happens in the full power charging, right? When you're in the light load charging or medium power charging, your efficiency is 80%. Nobody claims those numbers. If you look at most research groups, the way that they accomplish it. We need chargers that have high efficiency over the entire full load. From light load, 10% of the load, to full load, we want efficiency more than 90%, not 80% light load efficient and not, presenting this. Besides that, another subject that, in my opinion, needs to be researched in onboard chargers is the reduced stage onboard chargers. So, for example, right now we have an EMI stage, AC/DC stage, DC/DC. So can we get rid of one of those stages? Those contribute to the weight, volume, cost, efficiency. Right? Can we get rid of one of those stages? How we can accomplish this? In my opinion, either we use, new topology, we invent new topologies, or I think this is going to happen sooner or later, and wireless charging will push us coming to this end. How? Because based on the research studies that has been again done by the Bridgeless lab, they have found that wireless charging, if you want to have, if you want to have a stationary wireless charging, that's a subject, different subject, it's not that complicated. But if you want to have dynamic wireless charging is a wireless charging that you're driving on the road and you want to be able to charge your car, like you're going from a toll road, go from a specially designed toll road for a wireless charging car, and then you charge your vehicle during the travel. So then the best way to charge it is to have supercapacitors. Batteries, they don't have high enough power density to capture. So use supercapacitor as a buffer, and then charge the battery slowly. And then if you have a supercapacitor and the battery, you have two energy command and then a DC-DC converter in between. Now you can use the supercapacitor as an active power filter to regulate the normal battery voltage during the charging. So there are so many new things that we can look into, and the research community has not addressed any of these so far. Then integrated onboard chargers. Another thing, not only integrated onboard chargers, but integrated power electronic interfaces. For example, inside the car we have, as I showed, so many components I showed there. How we can integrate them? If we can integrate all these things, let's say have a power electronic interface, which is doing the functionality of the 2-3 converters at the same time. That is a new approach, right? For example, this is the example of onboard charging. Inside the car, we have an onboard charger to charge a 400-volt battery, right? And then we have an auxiliary power unit to charge a 12-volt battery, right? Every car has a 12-volt battery. Can we integrate these two and have one charger which charges both of them simultaneously? 50% lighter, 50% cheaper, 50% smaller, more efficient, bidirectional, no need to communication through CAN bus system as well. Tons of things, right? Also integrated high power chargers. So as I said, there are two ways that you can charge a battery, either an onboard charger or an off-board charger. Onboard charger, okay, this is what we talk. Off-board charger, the fast chargers. Now, if you look at the powertrain of a car, let's say Tesla Model S, it already has a propulsion machine 185 kilowatt and an inverter 185 kilowatt. Can we use that path? It's already rated for 185 kilowatt. Can I charge my battery by that 185 kilowatt power? But we need to reconfigure the propulsion machine and inverter. That's another way that we can, in my opinion, this is really attractive because right now, again, my personal opinion, I would love to discuss more about what you think. In order for electric vehicles to be popular, the batteries are there. Yes, one of the important subjects. Besides that, another thing is the chargers. So we need to have an evolution in the national charging infrastructure, right? We need to have enough fast charging stations, like gas stations that you can go anywhere. And that's not going to happen. Who's going to pay for it? Right now, Tesla is paying out of pocket to have all those fast charging stations. But I don't think all the car manufacturers will pay for it. I don't think GM is going to pay charge station or Ford is going to pay for a charge station. But what, in my opinion, could happen is private people come and invest, but that's going to take a long time. They need to look into their return on investment, they look into policies, so many things. But what if we can enable onboard high power charging with already available power electronics on board? All we need is an outlet. We don't need a full charge station. Charging station, we need only an EVSE called Electric Vehicle Supply Equipment. Okay? Only EVSE, and then charge the battery. So this topic, in my opinion, is very much interesting, and even though research community has addressed it, but has not received enough attention. We need the research industry, in my opinion, should push the auto industry to have a different look, because auto industry is very conservative and very slow in moving forward. And then, okay, besides those are, we need to look at the megahertz on board charging, because when we go into the megahertz, efficiency is difficult, magnetic components are difficult, but then they can make it very small. I'll show a megahertz level 3.3 kilowatt onboard charging stage that we have designed in my lab. It's not finished yet, but we are in the process of designing it. So the very first effort that we did a few years ago in addressing some of those items which I mentioned was Resonant bidirectional resonant parallel stage onboard chargers. So if you look at the DC-DC stage of an onboard charger, I'm going to, again, as I promised, I'm not going to be too technical. But this is a little bit, I'm going to go into some parts of it, go a little bit technical. So normally we have, this is the structure of an onboard charger, overall structure. Very simple. This is not the most optimal design, but it's one way of designing onboard chargers. In here, you have a very simple, let's say a totem pole. You can make it add another leg here, make it, or two legs, make it an interleaved totem pole bidirectional PFC stage, which is used for power factor correction, and ACEE certification. And then you have a DC-DC stage. Normally we have one stage here. Again, in most cases it's a full bridge CLLC resonant converter where you have two of these legs in parallel, and then you have inductor, additional inductor here, one magnetizing inductor here, an additional resonant capacitor here, and then output also you have a full bridge, whatever, and then you connect this to your filter, and then after filter you have your battery. But the way that we design these converters, again, I don't want to talk more on the topology, because topology can be full bridge, can be half bridge, different ways that you can design these things. What I want to say is that we only have one stage here, and that stage is normally a CLLC converter, which is designed for, let's say, full power. Let's say you want to design a 3.3 kilowatt onboard charger, and that's the way that you design it. But CLLC converters, they have their advantages and their disadvantages. And then we have, if you're a power electronic expert, you will see that this has 4 options: SRC, LLC, LCL, and LCC. You can analyze all of them, but then you will see that 2 of them, they stand out. One of them is LLC, one of them is SRC. SRC is really good at really high efficiency because all the components, you don't deal with the magnetizing inductor of the transformer. And also you don't deal with a lot of circulating loss. That's a good thing about LLC. But then, SRC, so efficiency is high. But then if you look at the gain curve, looking at the gain versus the frequency of the SRC converter, you will see that it's very difficult to regulate the output voltage. The problem with the onboard chargers is your value voltage active can go from 200 volt all the way up to 450 volt. So in the high voltage, you need to be able to regulate the output voltage, and the gain of SRC converter is always less than 1. The maximum point is, you can load adjust it based on transformer ratio, but you won't be able to regulate it in a wide range. That's why people are interested in LC converter, because you can easily provide the voltage, high voltage gain, low voltage gain, and play with the gain. But then, because you're taking advantage of the magnetic resonance inductance here, you're creating the resonant loss. So that's all I want to say. I don't want to talk too much of the technical thing. Now, if we can ensure, instead of having one highly rated LLC converter, we have an LLC converter, low power, let's say, we can optimize this design. We haven't optimized this, by the way. We only built based on intuition. What we did, we designed the 1.1 kilowatt LLC and the 2.2 kilowatt SRC. So LLC is always fully loaded, fully operational. SRC, we bring it up to the circuit depending on what is the charging power level. We look at the charging curve, and based on that, we can, plug it in or reduce it. You can improve the efficiency. So this is the prototype we built in the lab. By the way, this is not this huge. It is the height is the size of a mug. We should have done a mug because this way it looks so big. It's just a mug. And then we compared it with the state of the art. So we showed if you do this, our design, you can improve the efficiency significantly. In fact, we showed that at the full load, you can improve the efficiency by more than 1%. And by the way, this is only DC-DC stage, not AC-DC stage. And then at the light load, 10% of the full load, you can improve the efficiency by more than 10%, which is significant. This is really important. So this data that you see the bottom one, this is based on this paper, and then this is our capture data. And then, as I mentioned, we got interested in integrated onboard chargers. So this is the powertrain of a plug-in hybrid electric car. It's a very basic schematic of it. So it has an onboard charger similar to the one I showed you in the previous slide. And then it has a DC-DC converter to step down that 400 volt or whatever to 12 volt to charge the low voltage battery. And we have, in this topology, we have already an issued US patent and another pending US patent. So, as I said, two units, bulky, heavy, expensive, and they communicate through CAN bus system. And they have light efficiency, low efficient, making the light load, and also the power flow is normally in the vehicle, it's only unidirectional. You can only charge a battery. That's it. You don't discharge it to the grid application. So it's not compliant with the future grid applications. And also another thing which I should mention here is they need to communicate through CAN bus system protocol inside the vehicle. And then every car manufacturer has its own proprietary CAN bus protocol. That's another complexity. So, but if you can integrate these two, integrate to one component, you can have the integrated EV onboard charging, which is efficient over the full load, and also doesn't need to go through the CAN bus system, and it can provide grid support application. That's one of the areas which in my research group we have been working on it for the last 3 years. So this is the very first proof of concept we built in the lab. You can see the top is the control board. The very bottom one is the PFC stage. It's a bridgeless total volt PFC stage. And in the middle one is the Resonant DC-DC converter, which has a 3-wind transformer. This was a 3.3 kilowatt design we did. You can see different components we have optimized. This is not an optimal design. This is not designed which is for anything that we want. It's just a proof of concept that we can build in the lab. And then we look at the efficiency comparison, and we run a lot of analysis. We have 2 papers on this. One of them transactional vehicle technology, one transactional power electronics we have published, and those explain how we model, how did we analyze, and how did we compare with the price. Right. So this is the initial PFC stage, as you can see. We did some measurements in the lab, and we got at 1.9 kilowatt. At 110 volt AC, we can test it up to 1.9 kilowatt, which is level 1 charging. At 240 AC, we can go 3.3 kilowatt, get an efficiency of, you can see, maximum efficiency of 99.1, 98.2, and power factor is 0.99. And we compared it with the state of the art in these graphs. So you can see that this is during grid to vehicle charging at 110 volt, and that's during 220 volt or 240 volt. We did both results, and these are our own measured data, and this is what we got from the other people's work, and we just took some points from other people's work and then plugged and compared it versus that. And then you can see that we can get like about 3.5% efficiency in the 110 volt and 2% efficiency in the light load. And then also we did the same thing with the DC-DC stage. A unique, complex part of this design is the transformer. We have not only transformer design, but also design electromagnetically integrated transformer. So, because this is a CLLC topology initially we designed, so we have one leakage inductor in this side, one leakage inductor, one resonant inductor in one side, one resonant inductor in the other side, and then one resonant inductor in the tertiary. So we try to integrate all of them inside one transformer. So the design of the transformer took a lot of effort, and we have proven both like mathematically, analytically, and also using some finite element analysis that this works properly. So again, let's move on from these parameters that we have chosen to design, and these are just the comparison of the efficiency. These are the different things that we are just showing here, that the zero voltage switching happening, so we don't add additional switching losses. And you can see efficient number that we got in the peak efficiency 96 during the vehicle to grid and grid to vehicle charging, and during the high voltage to low voltage battery we get 93. This number should be improved. This is not good enough. This should go more than 94% definitely. But again, we are just in the research side of this stage. We are looking into different algorithms how we can improve it. When we did this project initially, we showed that this integration is possible, but we learned that this even though this is addressing many of the shortcomings that has not seen this integration, but one of the issues which is not being addressed is the preconditioning. Preconditioning means when you have a 12 volt battery on the car and a 400 volt battery on the car, sometimes you're at home sitting and you want to run your car, and the low voltage battery, if you're especially in the cold weather condition, your low voltage battery should run and warm up your high voltage battery, right? Sometimes you want to run both of them. So that creates complexity. You should be able to charge both batteries at the same time. Now, when you charge both batteries at the same time, in fact, you have 2 power sources in the output and another power source in the input. So you have 3 power sources, right? inherently there's going to be a current flow between these three. You can not only charge port 1 to 2 and port 1 to 3. There is going to be definitely a power flow between port 2 and 3. So we should be able to find a way to minimize that in order to improve the efficiency. Otherwise, either our efficiency is going to be low, or our power will be limited, or the stress on the components will be high and it will burn DC capacity. Or I need to oversize everything. So that was a challenge that we faced. And as I said, these are the things. So I explained all this past. This is the fact that we are talking about. We need to be able to charge both batteries. This is the Propulsion high voltage battery, and this is a low voltage battery. So I need to have a path like this, and reduce this if my car is sitting during charge station. But if the car is running, yeah, I mean, definitely you need to cut these and only do this kind of charging. And that's required during this kind of operation. Then both of them need to be charged at the low state of the charge, and we need preconditioning to warm up this battery or turn on these loads, in fact, to charge these things to run all the electronics on board of the car. So this is the main topology that we considered, and then we changed our topology. We thought CLLC topology is not enough, even though this might look similar to what we did in the past, but they are totally different topologies. This is not a CLLC integrated topology. Instead, this is called a triple active bridge topology. This is the control methodology of this is not pulse frequency modulation. In power electronics, only CLLC and resonant converters are controlled using pulse frequency modulation. But these kind of triple active bridge converters, they are controlled by pulse width modulation or by phase shift control, phase shift control. So the control algorithm is totally different. And you can see the different kind of components that we have, PFC inductors, and here we have the EMI chokes and CXCY capacitors, but then after that we have all these different components here. One of the uniqueness in design is to design a very compact, again, 3-winding transformer to be able to achieve that. And the control is a very important part of this. As I mentioned, we have 5 control variables in that we can control these 5 variables and achieve the minimization of the power flow between high voltage to low voltage during simultaneous charging of these two. So that if we assume that the phase angle of this leg is 0, Q1 is 0, and then we have 3 variables, delta 1, delta 2, delta 3, that these are the pulse width modulation, 0 time for the pulse width modulation for each of these signals that we apply. And also we have 2 other variables, phi 2 and phi 3, I don't know, yeah, phi 2 and phi 3. Phi 2 is the phase shift between the, if I assume the phase shift here is 0, then the phase shift between this leg and this leg's fundamental frequency is phi 2, and the phase shift between the fundamental frequency of this phase and this phase is phi 3. So we have 5 variables. With controlling these 5 variables, we can control the power flow, and we can control, for example, I mean, in this one case, we want to do the power flow for a variable range where the battery voltage is from 200 volt to 450 volt. And in this case, we want to also have another voltage. Mostly we are regulating the voltage in this case, because the voltage can go from 8.5 volt up to 14.8 or 15 volt. But in this case, we want to use, in fact, the LV battery as a buffer so that we can provide power to auxiliary loads. So it's a little bit complicated control strategy, and I don't want to go, I just want to show you the base of the control. And then we redesigned the whole board. This is the new board that we have redesigned. And then we are in the process of, we are interested in, right now we have discussed with companies like LG, and Faraday Future, and GM, and we are interested to translate this from university to industry. We are looking to. So this is the new board we have designed, and this is the new transformer. I'm not going to go through the detail of the transformer design because we have not filed for patent on that yet. But then this is the overall structure at the end, and we are closely working with the mechanical engineering department and people. They are helping us in designing the enclosure. So this is the design of the die-cast and package, as you can see. And we've spent tons of time in power electronics research. If you work, you would notice that unfortunately, most of us, we work isolated. We work on power electronics, but it's very important for us to collaborate with material science people, with control people, with mechanical engineering, thermodynamics, reliability people, and this is very important. So we have recently started working with thermal management and mechanical engineering people, and we are hoping to finish this design by January of this year, January of 2019. And then the whole volume, we are hoping that's going to be about less than 7 liters, which is smaller than a single onboard charger. But this is 2 converted inside, which can do the functionality of it. So those, as I mentioned so far, were on the integration of an onboard charger with the RTRU power module. Another subject I mentioned at the beginning is the high power onboard chargers, or I call it propulsion machine integrated onboard chargers. As I briefly mentioned at the beginning, if you look at the powertrain of an electric car, you will see that we have a big electric motor, big inverter. Some of them, they have a big DC-DC converter here, and then you have battery. You have this DC-DC, and then this. So the idea which I mentioned in the past was integrating this and this, these two together. Now, like another idea is like how we can use this instead of, we have also an onboard charger. How we can integrate these two and get rid of this and have an interface like this. So you can charge the battery, high voltage battery, just using this path, which is already there. So, to the best knowledge of mine, the cost of an off-board charger, if somebody wants to buy and install it, is about $16,000. So it's expensive, off-board high-power chargers. But we already have all these. All we need, just add a 3-phase interface here, and reconfigure the current flow in this propulsion machine and in this inverter, and potentially this DC-DC converter to charge the battery. If you can do that, the additional cost that you will add on the car, in my opinion, is not going to be additional, because this can also serve the job of this onboard charger. Is going to be 0 additional cost. So you don't add additional cost, you don't add any volume, you don't add any weight, you only enable. All you need in the charge station is 3-phase DVSE, which is going to be maybe $2,000, $3,000 in charge, but not $16,000. So we looked into this, and we designed very first proof of concept in the lab, initially for only 3.3 kilowatt. We tested in different scenarios. We got 92.6% efficiency, and most of our loss happened on the propulsion inverter. Most of our loss in that design was in here, which is already inside the car, not in our interface. But this could be improved, because this was the inverter that we bought was an IGBT-based. IGBT is like integrated gated bipolar transistor. And this could be, if this, you can improve this, then the efficiency can easily go more than 95%. So that's why we designed another prototype, which is liquid cooled, and for 10 kilowatt application. This is a very compact, and one of my students did this, and he did a really good job. Now he works at SF Motors. He joined SF Motors like a month ago. And then we showed that efficiency can improve, and this is not a correct number, maximum. This should be 95.5. And then we show the power density at 52 watt per inch cube. In this case, it's a 10 kilowatt power system, as I mentioned. Additional area of the research that we were focused on was the megahertz bidirectional. So all these things that I mentioned, these are really happening, and we're looking into the research level, and still we don't have exact answers, and the industry has not adapted to any of these things. But if you want to reduce the size of power electronic, there's no way unless you go megahertz, right? That's the thing. So power electronic community and onboard charging community is also looking at megahertz level power electronic interfaces, bidirectional chargers, power factor reduction. But the problem in the, I guess everybody, people who work in power electronics, they know what is the problem with the megahertz charging. Like, the issue is the cost, right? And also we don't have good magnetic materials. It's the area that energy is covering, and the magnetic material pushing to the switching frequency. These are some of the areas that we really, really need in power electronics. So we designed this to the best knowledge of mine. Again, I don't want to be immodest, but the best knowledge of mine, this is the smallest 3.3 kilowatt CLLC DC-to-DC converter which has been designed at this power level. And we have a paper which will be published, I think, it's been already accepted, it's under press on this work. It's a 3.3 kilowatt, the frequency is about 1.5 megahertz, and then the efficiency 97.2, and the volume, you can see it's very compact. Right now, we had some heating problem in this design, but now we are redesigning this to design a 6.6 kilowatt version of this instead of 3.3, and then this is only DC-DC stage. CLLC want to do a full 6.6 PFC and DC-DC, and the whole size we want to be at this much for 6.6. So the goal is to this power density that we have, about 151 watt per inch square. We want to hit more than 250 now. The goal is to make it 250 with the new design we're working on. So it's a PhD topic of another student of mine. So that's all I have to talk about the onboard charges. Now I'm going to move on and talk about other projects that we have recently completed. But if there is any question, I wouldn't mind to let you a little bit ask questions about the onboard charges, and I can move on to others. Yes.
Why haven't the car manufacturers already installed those on their vehicles?
The integrated onboard charge that I'm talking about?
Yeah, bidirectional.
So, bidirectional is a little different story. There's so many controversy in the industry. So some people say the auto industry is against bidirectional charging because the more you use your battery, especially bidirectional operation, you're going to reduce the life of the battery. So they're against them. So they don't want to have it. But it's going to happen sooner or later because to do grid support application, they have to be compatible with the smart application. So they need to incorporate it. Besides that, people have done research in Technical University of Munich or some university in Germany. They may not. They have done some research and shown that if you don't fully discharge these batteries, if you're using, let's say you're only using 80% to 100, 80% to 100, you're not fully going deep charging, you're not going to reduce the life of the battery. So that's exactly. So you should be able. So it's very difficult to educate other industries. I'm serious because I go to Detroit at least twice a year, sometimes more. I meet with engineers from Toyota, GM, Ford, Chrysler, all of them. They just want to continue whatever they like to do and they even don't want to team up that easily with any newcomer. They want to only work with tier 1 suppliers that they've been working forever. So it's very difficult. It's not like, it's not like, in my opinion, like Google. It's not like data center world that everybody is like everything is just being invented and they're open to this industry. But in my opinion, sooner or later they have to adopt companies like Tesla, companies like Faraday Future, companies like SF Motors, companies like Lucid Motors. They're going to push traditional auto manufacturers to get aligned with this. And these companies like Faraday Future, they are already integrating in their cars, the new car companies. Sorry, I talked too much about to answer this.
Thank you.
Yes.
Mark? Yep.
Thank you. Sorry, this board is blocking me from standing up. Thank you for the presentation. I'm Mike from United Silicon Carbide. I have a question on your sharing of using the inverter of the motor as the charger of the battery. So in order to do this, do you have to disconnect the motor while doing the charging?
That's a perfect question. I love to hear that question. I'll explain that. So a lot of people, they have looked into that, and then because the thing is, like, you don't want to charge, while you're charging the car, you don't want to run your car, right? Otherwise, it's going to be a disaster. So you need to find ways either to put relays, and those relays will be expensive and heavy.
Yeah. And also conduction losses.
And conduction loss is going to be high. That's ridiculous. I don't think it's going to be the way. And then people have looked at the ways to reconfigure. And in fact, one of the uniqueness of using this propulsion machine is that you can use the propulsion machine winding as a PFC inductors. If you put relays and decouple it, then you won't be able to use the PFC as a PFC inductor. You need to have additional PFC inductors, and that's going to add to your weight of the onboard interface that you add. So it's, in my opinion, out of the world. So the people that they have proposed that solution, in my opinion, that's not the way. Then there are other people that they have looked into solving this. By how? By designing a specially designed machines with 2 windings on their stators, which is going to be complicated. Already, you know how long does it take from the point that you start designing the electric machine to the time that you bring it to the market? 10 years. It's long, and nobody will adapt to that. It's not nobody's going to be too long. Now, another problem is people have looked into accessing the midpoint of the machine, midpoint of the winding of phase A, phase B, phase D, so that the current goes through each of these, and then the current is split between 2 parts of the winding, and the fluxes, they would cancel each other, so they wouldn't cause the rotation of the motors. This is possible. In my opinion, think is not the most preferred solution, because I don't think any electric machine manufacturer will build the electric machine and give access to the midpoint of the winding. And you can't even accurately find the midpoint of the winding. So the method that we have proposed, we don't need to release. We only configure the current path, but we have only access to the 3 points of the terminals. And we don't even need to have access to the midpoint of the winding. So we build an interface at the beginning, which is only active component, no passive component, only switches. And then these switches, the output of the switches will be connected to 3 terminals. So what I'm trying to say is that we are aware of that. So our solution doesn't. Only thing that in our solution, the rotor rotates by 12.5 degree and locks at that point, at the beginning. So no rotation, no full rotation. But thank you so much for bringing up. I forgot to mention that.
Thank you.
Yes.
In your conversations with the auto manufacturers,
do you hear anybody talking about moving to 800 volt or 1000 volt battery packs?
This is a very thing. 4 years ago, I wrote a proposal to theory. I wrote a proposal theory on this subject of moving to 800 volt or 1000 volt, and my proposal got killed. They said no, it's not going to work. And now I see everybody's moving to 800 volt, especially in the high performance vehicle. That's normal right now. Everybody, they have to go to 800. Otherwise, the thickness of the cable is going to kill the weight. It's going to, obviously. And in my opinion, yes, everybody is moving, especially with the fast charging technologies which are happening. You know, this DOE has extreme fast charging call for proposal that they are looking into 350 kilowatt. If you go 350 kilowatt, if you do 400 volt, you know how much is the current? It's going to kill the battery. You have to go. They are not there going. So I'll move on to go through, briefly mention other projects that we have recently completed. I promise you it's not going to be more than 5 minutes. And then I'll be happy to discuss more questions. Yes, 5, 10 minutes. That's more than 5 minutes. So one of the areas that we have been working with Boeing on the silicon carbide-based regulated transformer rectifier unit. So what is regulated transformer rectifier unit? Regulated transformer rectifier is like an auxiliary power supply. So inside the vehicle, we have a 12-volt battery, which runs out of that 400 volt. Inside the vehicle, inside the airplane, you have a 28-volt battery. If you're sitting on the plane and you're flying anywhere, you're watching TV, you're listening to music or air conditioning, they all run on 28-volt battery. So the jet engine is normally coupled to a generator. That generator output voltage is a variable voltage, variable frequency, 3-phase, and that needs to be converted from 28-volt to supply the auxiliary load. So we designed that. And then we worked on a DC-DC converter, GaN-based, to design a maximum power point tracking and also modular PV micro converter for space application. We worked with a space company that I'm not allowed to mention the name, but yes. But then, and also we worked on the miniaturization of power electronic for biologically inspired microrobots. Also, we've done some work on pyroelectric energy harvesting. In terms of the silicon carbide-based regulated transformer rectifier unit, as I said, aircraft, they need to have a 28-volt system. We designed what we did. The innovation of our design was not mainly on topology, because the topology was initially an EMI stage, followed by a 3-phase boost topology, active boost, and then followed by a DC-DC converter, which is phase shift full bridge, very simple, with a center tap transformer at the top. So we designed this using silicon carbide. We showed a 95.4% efficiency, 4% total harmonic distortion, and 0.99 PFC. And then the uniqueness of our design was we came up with a very, my student came up with a very novel method to find out the frequency of the converted operating frequency of the converter to attenuate the electromagnetic interference by proper design of the EMI filter. And then that's why we came up with this topology, which the EMI stage is only 1 port, 1 pound, and it's very complicated to do. That's because the other work that we have done was, I think it's the KTH. They've done this similar power level using a matrix converter, and their EMI stage for the same power level is 5 times more than 4 in terms of weight. And this one we completed for Boeing. Boeing was very happy with our result. In fact, this is some of the results that we have gathered. And you can see that the input is 234 AC, the DC link voltage goes to 600 volt, and then this is operating frequency is 100 kilohertz. This stage gives 98.5 efficiency, and the BMI is 99.8. It's air-cooled. And then this gives you the power split, which let's move on. And then this is the second stage, which is a phase shift full bridge topology. It's very simple. Again, 100 kHz switching frequency. And again, this is the power step. And then finally, we could comply with the EMI really well, and they were happy with this, so they decided to work with us. And now we are collaborating with them to design a separate, now a new gallium nitride version of this topology. So this is silicon carbide, we want to go gallium nitride because we want to improve the efficiency, reduce the weight by 30%, and also the goal is improve the weight by 1%. So right now our total efficiency is 95.4, we want to hit 96.5. And then we are trying to reduce the weight and volume by 30%. And then, but the topology also changed. We have totally new topology, totally new approach to the gate drive, and also analyze. It's under investigation. We just started this project. Also, we did this for the gallium nitride for PV microinverter applications, and we showed a 3.7 watt per gram power density and 98.5% efficiency almost. So one of the unique things about this topology is that because this was meant for the space application, and the temperature could go from negative 120 degrees Celsius to positive 40 or 50 degrees Celsius. So it was very important for them that we designed something which can operate in really low temperatures. So that's why we use GaN, and GaN apparently has a better performance in low temperature. And they tested this. It went through I don't know how many cycles, but they tested this. I think they put on the life cycle and accelerated testing. I think failed. I don't know after how many thousand cycles, but the reason that it failed was because of the microprocessor failure, not the switch failure, because it couldn't operate in the low temperature for a long time. But it was a really good demonstration for proper operation of GaN at low temperatures. Also, we work on the miniaturization of power electronics for micro robots. In fact, one of my colleagues, Professor Sarah Bergreiter, she works on these biologically inspired micro robots. If you look at many of these micro robots, in fact, YouTube, you can look at the Robert Woods group, for example, they're working on the flying micro robots, or Sarah's group, they're working on the jumping and walking micro robots. One of the very interesting challenges, if you look at it, the micro robot is smaller than a fingerprint, but then their power supply tend to be bigger than the robot, because the fact is like the voltage, the battery that they can carry is 2-volt battery. But then if you have a micro robot, let's say, I'm just giving an example, let's say a flying micro robot, right? You need a high voltage with a sinusoidal or trapezoidal or square wave drive signal, so to actuate one wing and then actuate the other wing. First of all, these are mostly capacitive, they have capacitive nature, so they don't completely consume the power which is given to them, right? So you have to waste it. Second of all, if you're not using it, you can, you need to step it up and create this, and then also they don't utilize it, right? So you need to go through a 2-stage power electronic design. One step up, one inversion. So these 2 stages, they can operate in maximum efficiency each of them. For example, if the step up is happening, let's say I'm just giving a hypothetical example, 70%, and inversion at 50%. The total efficiency, if you can operate each of them in the maximum efficiency, is what? 35%. Efficiency is not good. And then they're not bidirectional, so you waste whatever power is not, energy is not used in the capacity actuator. So the best approach would be maybe design a single stage which can do both step up and inversion in a single stage. Maybe you can get 70% efficiency instead of 85% efficiency. But also you can make it bidirectional, so you can utilize the unused energy give it from one wing, give it to the next wing, or take it from one wing and put it back in your energy storage components. So, and also miniaturize these power electronics. So that's another area which we did some work, and we designed a converter operating 1.5 megahertz and with 75% efficiency. To the best knowledge of mine, this was the first paper published in Transactional Power Electronics, which was related to miniaturization of power electronics for microblock. We also completed that. Also, we designed some miniaturization of power electronics for electromagnetic energy harvesting, and also, we worked with a company called Altenera. They have these tiny wind reed, they call it wind reeds, that they want to harvest power from the wind vibration. So their voltage depends on the wind speed, it could be very low. So then the traditional direct bridge wouldn't work. So we came up with a new Resonant, quasi-resonant AC/DC step-up converter. We designed that for them, and we did the 6-channel version that we could put six different wind reads similar to a solar cell, 6 solar cells, for example. We also worked recently. We did a project with pyroelectric energy harvesting, which is focused on harvesting power from thermal gradient, right? So people have looked at the thermal gradient energy harvesting. This pyroelectric materials, I wasn't familiar before this work. I just recently became familiar. You normally charge them from certain voltage to certain voltage, then warm it up, discharge it, cool it down, and during this process you can harvest power. We designed a power electronic interface and demonstrated for the first time that you can charge a battery using the pyroelectric cycle. And that's my presentation. This is another project we did with a company called Genovation that they built the world's first electric Corvette. It's the fastest electric car in the world, to the best of my knowledge. It has a top speed of 220 miles per hour. They are local in Maryland, and we have 2 patents out of this version. This is real car. It's not like just a concept, and they have tested it. You can look in YouTube or Google. You can look the proper. So, and I would like to acknowledge some of our sponsors. Thank you for listening to this talk. I'm sorry if I went a little bit over past time.
Thank you, Alireza. Any questions? Follow-up questions?
Hi, Professor. Thank you for your presentation. It's a very great presentation. Actually, I'm working on a multi-port converter right now, so I'm very interested in your 3-port converter you showed before. So I see that in your presentation you use pulse. You regulate the voltage as a pulse instead of square wave, but actually in my experiment, I will have maybe like 10 ports or even more, but I regulate all the voltage as square wave. So I want to know so what the benefit you can gain from the pulse wave voltage?
So you want to see what is the benefit we can get from the delta?
Yeah, right. Right.
So to be honest with you, the delta, because our case is a little bit different than your case, because Professor Chen explained to me the project that you're trying. You have advantage in our case in comparison to us because your output voltage is fixed.
Oh, okay.
But our output voltage is variable.
So you run it as like a LLC?
Yes.
Okay.
Because we have variable output voltage, that makes our life a little bit difficult. That's the advantage we get from the delta variation.
Okay. So can you keep all the switches in soft switching all the time?
Not all the time. Depends on the power level. When you go to lower power, it's a little bit difficult to sustain. Right? In higher power, it's easier for us to get the 0 voltage switch. But when you go in lower power, sometimes we lose.
Oh, okay.
Yeah.
I see. Thanks.
Any other question?
Sure. Thank you. I'm from the industry.
Sure.
Microgrid, did you work in any applications in the microgrid specifically?
Not unfortunately. No, I haven't worked on the microgrid. The closest I am working is this. We are trying to finalize the design is this bidirectional charger to be integrated with the grid. We have, and then we just recently got a DOE grant to build microinverters, reliable microinverters. So that's the closest. But most of my work, you can see it's not really integrated.
Thank you.
Any other question? If not, I will ask a question. Sure. You mentioned the V2G and the high power charger. One of the challenges of this fast charging is that you cannot get enough power from the grid.
That is true.
So what do you think will be the strategy, like full system strategy from the grid all the way to the vehicle? Like how can we get enough access?
So it's a little bit not in our hand, right? Because if you want to get the power from grid, sorry, I'm moving away because I'm moving away so that light is not right in my eye. So when you want to get the power from grid, we are assuming that the power is available, right? If the power is not available, we can't do anything. So I'm not an expert in grid, but all I can say is like eventually if you look at the distributed generation, what it means is like you have a distributed generator, right? You have a local solar system, wind system, and energy storage system. Then that is going to be able to provide enough power to charge up to a certain amount of EVs, right?
Okay.
For the fast charging. And then we are not going to do fast charging all the time. I don't think we will do fast charging because us as a single user, we don't want to, first of all, when you do fast charging, you're going to pay more, right? You're going to pay more. Second of all, you're not going to have access to fast charging everywhere. You will do fast charging and you're going to reduce the life of the battery. So we're going to do fast charging most of the time when we are doing long trips.
Right.
Yes, during long trips, yes, we can do fast charging, but if it's, other than that, we will mostly do overnight charging, which is okay for the grid in my opinion.
So basically, like this kind of ecosystem, solar, battery, microgrids, and EV
That
could be
should
an ecosystem,
happen.
but it doesn't need to be everywhere. It could be.
Exactly. That's what I think.
Right.
Again, that's based on my.
Got it. All right. Oh.
Yeah, I'll just second what you said because it's my impression that the whole thing about 350 kilowatt chargers all over the world, everywhere, it's a myth being created to slow down the progress of this EV industry. Like he says, if you actually own an EV, nobody charges at 350 kilowatts all the time, right? You do it for long trips on the weekends and stuff like this.
Exactly.
Most of the time, if you have access to a 50 kilowatt charger, you'd be going plenty fast enough for everything you need to do on a day-to-day basis. Even that you probably don't need, but 50 kilowatts would give you a really, really nice, sweet
Exactly. I
operating
completely
point.
agree. And I second, in my opinion, 11 kilowatt itself, it's most of your daily commute at home, going to work and coming back, and 11 kilowatt. That's enough. Unless, again, if you're going to do long trip, you're going from, I don't know, Washington, D.C. to San Francisco or something, then you need to do a lot of fast charging. Otherwise, I don't think.
Yeah, and that infrastructure is also necessary to
That's
build.
definitely necessary.
It's not such a backbreaking problem
Yeah.
if you think about it from the realistic use point of view.
Of course, yeah.
Right.
But from DOE perspective, I think they use this as kind of a motivation to drive the academia and industry to push towards that limit because you can find other applications where you need fast charging anyways.
Sure.
Right.
That all makes sense. So let me just ask you one last question. We work with people who are doing onboard chargers, and we work with some companies now in the US that are betting on wireless charging. Where do you think these types of things will, will wireless charging become big? In what areas do you think that'll be successful? Or is it all just going to be plug-in type charging?
In my opinion, wireless charging is going to be very popular, in particular, static wireless charging. Dynamic is going to happen, but it's going to take a long time. Because I don't know who's going to pay to electrify roads. Right? Electrifying roads needs so much money, so much infrastructure. But static charging is going to happen. The issue right now with the wireless charging is the weight and cost of wireless charging. To the best of my knowledge, again, I'm not talking from an industry perspective. To the best of my knowledge, the cost of a wireless charging is, I think, 3 to 5 times more than a conductor charging. So that is prevented. Already electric cars are expensive. Now if you want to have another component which is 5 times more expensive than the other solution, people would rather to go with, I don't know, again, to me, if I'm buying a charger for my cell phone, I would rather to pay $10 as opposed to $50. So I think, again, if as a whole, if you can bring the cost of the system down and show the benefits, yes, the convenience of the wireless charging will make sense. But if the price difference is only, let's say, 20%, 30%, maybe. But if it's 5 times, it's going to be a little bit difficult. But in the long term, it's going to happen because autonomous driving, autonomous cars will push other industry to go through wireless charging. It should become wireless, but it will take time. It's not going to be fast because of the cost factor. Again, that's my opinion. But
yeah. But in the idea that you have of dynamic charging, there are projects I'm aware of where in an Amazon-like warehouse, you could have a track
of course
for the robots that pull packages up and down, which is dynamic. The current method is in some factories is, you've got a thing that comes up and stops. Every time it's idling, it's wirelessly charging. But this other method that you're thinking about probably would be even better. It's just perpetually.
So for golf carts or for, let's say, even buses, it's more feasible than passenger cars. Because they are all the time, the buses are stop and go, stop and go. But for passenger car, it will take difficult time to electrify the entire road and then put supercapacitors to harvest that power in a very short period of time. Okay. Yeah, so we need to, not only need to electrify the road, but also you could change the energy storage system of the car to the supercapacitor, or somebody needs to invent a very high power density battery. That's what the research limitation. Thank you. All right.